All right, here we're looking at a problem that involves friction. This problem says I'm pushing a crate with an angled force as shown, and the picture shows that I'm pushing down and to the right on the crate. Will the crate slide if I push with a 100 Newton force? And what is the biggest force that will not make it slide? All right, so this is primarily a Newton's second law problem. So I'm going to write that up here and explain A. And I'm writing in that the sum of the forces is equal to mass times acceleration because that is Newton's second law. All right, so I gave the name and the equation for the physics principle that we're using. All right, so I'm going to start, because this is a Newton's second law problem, I'm going to start with a free body diagram. So here is my crate, and I want to include all the forces that are acting on the crate. So we have a gravitational force that acts down. We have a normal force that pushes up on the crate. The normal force pushes away from the table because that's what normal forces do. Gravity is from the Earth. We are told that there's a friction force, and that friction force is going to try to prevent the crate from sliding. And if there was no friction, it would slide forward. So the friction force tries to prevent it from sliding, so the friction force is going to point backwards. And we have the applied force F. And that one is forward and down at an angle of 15 degrees. Okay, and we want to know whether or not it's going to slide. So in order to figure that out, what we're going to try to figure out is what friction is needed to keep it from sliding. And secondly, what friction is possible. Those are the two questions I need to answer to figure out if it's going to slide or not. So to figure out what friction is needed to keep it from sliding, we're going to assume that it doesn't slide, which means that if we add up all these forces, we should get an acceleration of 0. I'm going to pick a coordinate system where the x direction is forward and the y direction is up. And we're going to say that if we add up all of the x components of all the forces, it should equal mass times the x component of the acceleration. And if we add up all the y components of all the forces, it should equal mass times the y component of the acceleration. To find all the x components of all the forces, we're going to say that the F has an x component and a y component, and the x component is going to be the one that is adjacent to the 15-degree angle. So adjacent means cosine. So we get F cosine theta minus friction equals 0, because remember, we're going to assume that it doesn't move and figure out how strong friction has to be to keep it still. And in fact, what we figure out is that in order to keep it still, friction has to equal F cosine theta. So friction should be equal to 100 newtons times cosine of 15 degrees. And that is 96.6 newtons. This is how much friction we need to keep the object from sliding. So, how much friction do we have available? Well, the maximum static friction is equal to mu sub s times the normal force. That's the maximum possible static friction. So if the maximum possible static friction is more than the needed static friction, then it's going to stay still. It's not going to slide. If the maximum possible static friction is less than the needed friction, then it will slide. So how do we figure this out? We need to know how big the normal force is. To figure that out, let's look at the forces in the y direction. The normal force is up. The force of gravity is down. And a component of the push, that F force, is also down. And let's see, let me go ahead and draw in some components here. We can see that the F force pulls forward, but it also pulls down. And the part of the force that pulls down is opposite the 15 degrees, so that means F sine theta. And those three forces should add up to 0 because there's no acceleration in the y direction, and this tells us that the normal force is equal to the force of gravity plus F sine theta, which means that the normal force is equal to force of gravity is mg, so that is 20 times 9.81, and the applied force was 100 newtons times the sine of 15 degrees. So our normal force is 222.08 newtons, which means that our maximum possible friction force is that times the coefficient of friction, which is 0.6. So the maximum possible static friction force is 133 newtons, which is more than the friction force needed to keep the object still, which means the object will in fact stay still. Now, friction's not actually going to push with 133 newtons. Friction's going to push with 196, because that's all that's needed to keep the object still, to keep the object from sliding. And friction will only push as hard as it has to keep the object from sliding, if it can. And this 133 newtons tells us that, in fact, it can. Okay, so the next question is, what is the biggest force that we could push that would not make it slide? And you might think, well, we just need to overcome this 133 newtons. But that's not quite right, because the harder I push, the bigger the normal force is going to be. So if I push harder, I'm going to have more normal force, which means I'm going to have more maximum friction. So I can't just use that 133 newtons. What I'll have to do instead is go back to basically these equations. Because the picture hasn't changed. So if I look at these equations, let's see what we can do with that. I'm going to start here, and this tells me that F cosine theta should equal the friction force, should equal the maximum possible friction force. okay? Because if I want to find the biggest possible force here, I need the biggest possible friction, okay? So that means that F cosine theta should equal mu sub s times the normal force. Okay, and we know that the normal force is equal to the force of gravity plus F sine theta. So now all I have to do is solve this thing for F. So let's multiply out the mu s. So that's mu s, and let's make the force of gravity mg plus mu s F sine theta. Now, to solve for F, I'm going to get all the terms with F on the left and all the terms without F on the right. So I have F cosine theta minus mu s F sine theta equals mu s mg. And now I'm going to pull out the F. So F times cos theta minus mu s sine theta equals mu s mg. Divide both sides by the thing in parentheses, and I get my equation that says the biggest I can push without making it slide is going to be equal to mu s mg divided by cos theta minus mu s sine theta. And when I plug that in, I get, what do I get? I get 122 newtons. Okay, well, so that's solving the problem, but what did I do? What did I use in doing this? Use Newton's second law the whole time. Did I use any special case equations? Well, let's see. I did. I used that right here, the maximum possible static friction, Fs equals mu s times the normal force, because, let's see, why did I use maximum? Because I needed to know, because I needed to know how strong friction could be. Did I use any other special case equations? I guess so. Right here, I used the force of gravity is equal to mg, and that's because we're near the Earth. Let's see. I think everything else in here was just algebra. So those are the only two equations that I used when solving the problem. Okay, did I plug in any numbers that were not explicitly given in the problem? I did not. There were no numbers plugged in. The only numbers I plugged in were the coefficient of friction, the mass. Oh, I guess G. G wasn't given in the problem, so all right. G equals 9.81 newtons per kilogram because we are on Earth. Okay. Theta was given, coefficient of friction was given, mass was given, so nothing else was plugged in that wasn't explicitly given in the problem. All right, put my answer into context. Well, here I'm going to say the maximum force that doesn't make the box slide, that is 122 newtons, is more than the applied force in part A, 100 newtons. Okay, and this is actually an interesting point for our evaluations. We are trying to compare our answer, and Fmax was one of our answers. This 122 newtons was one of our answers. It was the maximum force that didn't make the box slide. And the appropriate reference value that I decided to apply it to was something that was given in the problem. The problem gave us a force of 100 newtons, and then it asked us to find a different force. Well, that's a perfectly valid thing to compare it to. So I compared it to 100 newtons, and that was the applied force in part A, and I found that the answer was more than the applied force in part A.